Nice to see you all again for the Scottish Data Science and Technology Meetup. I'm Chris McFadgen, Head of Data Science Recruitment at NBN Solutions. I'll be hosting tonight's event. We're pleasure to be joined by the Data Science team at Optima Partners. So we're going to hear tonight from Manjula, Scott and Jana on data science beyond packages and libraries. I'll let the guys introduce themselves in the business in just a second. We're going to have all the presentations back to back, and then we're going to follow that by Q&A. So if you need to help yourself to a drink, a bite to eat during the presentations, then that's absolutely fine. We've got the fire exit just behind this wall here, and obviously toilets, the ladies on the left and the gents on the right. And yeah, we'll finish up with a bit of networking and more beers and pizza if you fancy it. I think we'll get started. Cheers.
Thank you. Hi all. My name is Manju Disanaika, and today I'm going to talk about data science beyond packages and libraries. But before I dive in, let me briefly introduce you to my background. So my first degree was in medical microbiology, but I've always been interested in computers. So I decided to change my direction and go into computer science. So I ended up doing a PhD in AI, specializing in evolutionary algorithms. And then I did a little bit of postdoc research in renewable energy. And then I moved on to doing some industrial software engineering. And then I moved on to doing data science in financial services sector. And now I'm with Optima Partners. And I'm excited to be with Optima Partners because Optima is tackling some really interesting and topical problems at the moment. So it's a very exciting time at Optima Partners. So the main question that I'm going to be tackling today is, should data scientists be engineers as well? So I'm going to be exploring a few themes today, and at the end, I hope to find an answer to this question. So first of all, can somebody tell me what that device is? Disclaimer, it's not 4th generation Oculus Rift. Anybody? All right, well, it's a handheld ultrasound scanner, mainly used in cattle. You'd be surprised how much science, especially data science, is going on in a simple dairy farm. They need to monitor these animals very carefully. And one of the ways of doing this is by using a handheld ultrasound scanner. Now, in the UK, these things are used by trained vets, so they know exactly what they're looking for and they know exactly what they're doing. But in other countries, especially in the United States, they are sometimes used by untrained people. So the company decided that if you annotate the video stream, it would actually help the operator. So if they're looking for ovaries, for example, in the live video stream, when you see an ovary, if the word ovary comes up, then the operator knows, okay, let's slow down. I found an ovary, let's look more into it, right? So this task was given to the data science team, and they came up with a solution to build a machine learning model to classify each frame in the video stream. This solution worked well. It had great accuracy. They did a demo to all the stakeholders. Everybody was happy. So they were asked to deploy this solution to the production system. Now, there's a problem. So the production system in this case is actually your mobile phone, which you download an app onto, and then you tether the mobile phone onto the device, and the device sends the video to your mobile phone. In the demo, they used a desktop machine, which was far more powerful than your mobile. So when they started using the machine learning model on the mobile device, they had a problem. So the video was being streamed in 30 frames per second. Each frame was taking 50 milliseconds to classify. You can do the math, and you have one of these moments. It was never going to work. So they had to actually take the model apart and rebuild it. But they managed it. They managed to fit this into a mobile device. So the moral of the story is the packages and the libraries that you use in data science and the models that you build should be guided by context. You need to be aware of where your model is going to run, which users are going to use it, how interactive it needs to be, how fast it needs to be. And if you think about this, it will actually guide the libraries and packages that you use for building your model. And they could have actually saved a little bit of time if they'd planned properly from the outset. So the context really matters. So the next theme that I'm going to explore is optimizing as you go. Now, I'm not talking about optimizing from a machine learning or data science point of view. I'm talking about optimizing your code. So for example, if you were given a task to track active customers in a fintech on a 15 or 30-day rolling period, there are a couple of various ways of solving this problem, right? But context, again, is very important. This data goes straight into exec dashboards. Execs use these dashboards daily to guide the business. They go straight into social media platforms like Facebook for direct marketing. We use them for foreign exchange rate experiments, and we also use them for customer churn models. So it is really quite important to get this right and to deliver the data on time, right? So we have two ways of doing it. Right, on the left-hand side, first way of doing it is basically a series of nested for loops. Now, this is quite intuitive for a data scientist because this might actually be the way you visualize the problem in your head, right? So first of all, I need to go through all the dates, then I need to go through all the users, etc., right? So regardless of the language that you're using, you might jump into code, use for loops, and solve the problem, and it would work without a problem. There's another way of doing this, and that's using some tools available in Python. So you would use data frames, and you would do rolling sums on these data frames, and then you would run a lambda function on top of your results to tag customers. So any ideas which one of these methods is going to be faster on a fairly large data set?
I'll vote number 2.
Number 2, very. This was done in Python. Number 2. Okay, very good. And that's the difference. So for loops on about 100 million transactions was taking 8.5 hours, and the Python way actually only took 16 minutes. So that's a huge improvement, right? So it goes beyond your programming language. So we spoke about R and Python, but it applies to other tools as well. For example, Oracle has this tool called SQL Loader. When you run this on the terminal, it's orders of magnitude faster to ingest data using that tool than any other available method. So the summary again is that you should optimize your methods as you go because the gain is going to be huge. You don't need to go to the nth degree and micro-optimize everything. You should just aim for the low-hanging fruit. So just a little bit of research will get you a long way. And the next theme I'd like to explore is logging stuff. So again, I'll illustrate this with an example. Here we have a production system that's spewing out a lot of data, and we have a Python program that is ingesting this data and doing various things with it. So it does AML monitoring, for example, compliance checks of customers, fraud detection, and it also feeds data into BI dashboards built in Shiny, right? Now, on production system, if this starts misbehaving, for example, if it starts crashing intermittently is the key word here, it's going to be very difficult to debug this, right? So as a data scientist, if somebody tells me, right, this thing is failing intermittently, can you please debug it? The first thing I try is that I try to run this on my local machine. But if the problem is something to do with, say, for example, RAM, you are guaranteed that you're not going to be able to reproduce the problem on your local machine because it's next to impossible to replicate the load profile of your production server locally. So you actually don't know how resources are used on your production server, right? So you need to fall back on your logs to observe what's going on the production server. So what I would do is I would introduce a logging framework and log sensibly, especially entry and exit points in methods and chunks of code that you think are going to be resource intensive. And then you would deploy this into production and monitor it for a while. The next time it fails, you can look at the logs and it will tell you exactly where it failed. And then usually once you know where it's failing, solution is trivial, usually, right? And the other advantage of logging is you can put a log analyzer on top of this. So as long as your logging is standard, it's formatted in a standard way, log analyzer can run on top of this, pick out specific events. So you can program the log analyzer to send you an email or an SMS Because if you are making customer-facing models, you need to be one step ahead. You need to know that your model is failing before customers notice, because by the time customers notice, it's game over, right? So this is the importance of logging stuff, right? And the next thing I'd like to talk about is testing. Now, testing in software is a huge area, and I'm not going to cover everything because there are various aspects to it, but I'm going to talk about unit testing. Because as a data scientist, you are directly in charge of your unit testing. You can write your unit test as you write your modeling code or your data wrangling code. So why is this important? Because it saves you time. This is a little bit counterintuitive because you might think, oh, how can it save me time? Because I need to spend a lot of time setting up my tests, right? But once you set up your tests, as your model and your data pipeline grows in complexity, debugging becomes much easier with your tests. So if you need to add a new function to your pipeline, for example, if your tests are written in such a way that it is actually testing the expectations or the core logic of your system, when you add a new function, if you break the core logic, your unit test will catch that. So you actually have the freedom now to go ahead and quickly add stuff, knowing that it's not possible for you to break the core logic. You have a safety net, and it lets you spot mistakes very early. But a hidden advantage of unit testing is that they act as documentation. Now, testing usually is much easier to read than your production code because testing is exploring the expected behavior of your code, right? So they are written in a more verbose way, so almost always it's much easier for you to read your tests as you would do a normal paragraph in English, basically. And because they are testing the expectations of your functions, if you read your tests and then go ahead and read your functions, you know exactly what to expect from your function, because the function code can be quite nasty and quite complicated. And if you know what you're looking for, it's much easier for you to make sense of that complicated code. So that's one of the biggest advantages of testing. And the next topic I'd like to talk about is managing dependencies. So let me take another example. So let's say that we are managing a data science project, and this is written in R, so we enable Renv on it. Renv is a package in R that lets you manage your libraries. And the usual way you use Renv is basically you initialize your project, let developers develop as they normally do, and at some point they call a method called snapshot. What it does is it scans the entire project for changes in your dependencies, and it writes the dependencies to a file called the log file. And then you push your code up, and what happens then is other developers can pull the code down and sync their environment to be exactly like the intended environment, right? So let's put 4 developers onto this project, and one of the developers goes ahead and makes a change to a package. But this developer doesn't actually snapshot, but commits the code. And what happens at this point is that for these 3 developers, the code is broken, but they might not necessarily know their code is broken, because in a typical data science project, you don't run all the functions all the time. So you might have broken code without realizing that it's broken. So to make matters worse, somebody else might go ahead and do exactly the same thing and push their code up, and at this point, the original author's code is also broken. So the entire repository is now in various stages of brokenness without you realizing it. And then they try to push this to production. And production is completely broken because production is expecting the log file to be up to date, right? And in a complicated data science project, pinning this down to exactly which version of a package led to the breakage is very time consuming, and it's very complicated thing to fix. So using something like Renv and managing your dependencies properly can save you a lot of headache. And this leads me nicely to version control. So the previous problem can be compounded if all 4 developers were actually committing to the same branch. So now you have broken packages and everything. So unpicking this becomes really, really difficult. So data scientists are really good at digging into stuff, right? So when given version control, they might start digging into this thinking, right, I must think about my branching strategy. Should I use 1 or 2 long-lived branches? Should I use a merge or a rebase? Should I force linear history in my repository, etc., etc.? You can make version control as complicated as you want it to be, right? You should stop there. You don't need to go that deep into version control. You can actually be a Git ninja with a handful of commands. So if you understand the concept behind these commands, and then if you go and find a nice GUI that actually lets you do these commands, you'll be a Git ninja. And if you want to go one step further, you can master a couple of more commands and you'll be a super Git ninja at that point. So for example, I use the stash command all the time because I usually work on multiple branches at the same time in my repository. So if I'm working on this branch, it's a problem for me to leave that branch and go to another branch to work on something else. That's where stash comes in handy. So, version control, when implemented properly, can really save you a lot of time, and it makes your development process much easier, and you don't need to go to the nth degree on it again to be good at it. So, before I explore my next theme, can anybody tell me if they've seen this before? What's cookie cutter got to do with data science? Basically, this is a way of putting order into chaos. And by that, what I mean is cookie cutter is a tool that lets you create standard repositories. Okay. Now, putting standards in place is very important. Now, I've seen our projects where there are 5, 6, 7 authors. Each author contributes a script, and each script has imports at the top. So, for you to try to figure out exactly how many libraries are used and how many versions are used in your project is difficult, let alone managing it, right? So what you can do is you can put a standard structure down and you can say, right, here is a script that I'm going to use to import all my libraries. Nobody else is allowed to import anything outside this script. So just by opening this script up, you know exactly how many packages are used in your project. Right, so this is why structure is important, and then you can enhance this by adding a logging framework and a testing framework, and you can write a nice README file, and that explains exactly how this project should be cloned and how it can be run. And then the last trick is basically getting everybody to use it. So if you're brave enough, you can have a go at it at this, getting everybody to use it. Other things that we should talk about are Docker and MLOps, but we don't have time today to talk about them. But I'm always up for a good chat about these technologies. So if you want, just drop me a line and we can have a chat about them. Going back to the original question, should data scientists be engineers? Well, in my opinion, absolutely. Of course, you don't need to have a VSc degree in software engineering. You just need to master a few basic concepts and use common sense, and it'll make your life a lot easier. Thank you. Scott, all right. Thanks.
There we go. All good. Hello everybody, my name's Scott Perry. I'm lead data scientist at Optima Partners. I'm a mathematician by training, and I've worked in financial services for probably close to 12 years now in various different guises. Most of the jobs relying heavily on data. Started life as an actuarial trainee and decided didn't want to be an actuary anymore. Got told I had too much personality to be an actuary, whatever that means. Take it as a compliment, but never mind. And then sort of meandered through customer experience, meandered through analytics, ended up in commercial analyst at Sainsbury's Bank, joined Tesco Bank where I met Dan, who's now the new boss at Optima Partners, go figure. And despite what the introductory slide said, I'm not PhD yet, but I'm working on it. That's coming next. So I'm starting my PhD actually next week, which is going to be really fun and really exciting. So data science is one of these slippery concepts. It means something different depending on who you ask. But some chap back in 2013 came up with this Venn diagram, which I think everyone's seen at some point in their life, where they basically say data science consists of these sort of three main themes, where you've got your coding skills, you've got maths and stats, and sort of subject knowledge. And really, what I want to talk about today is how can we make sure that data scientists are equipped with the right skills and the right abilities to be the best at what they do while avoiding this danger zone. So data science has a massive effect on people's lives, and it's becoming more and more apparent these days because data science is in so many industries. So like doctors, they are, what am I trying to say here? So doctors in the UK, they are required to be part of the General Medical Council. You've got to be registered with the General Medical Council to practice in the UK. If you look at actuaries, accountants and auditors, they are also regulated by the Financial Reporting Council. And if we look at the chartered surveyors, they are regulated by the Royal Institute for Chartered Surveyors. So what is it that sort of resonates with all these three professions? So it is, they all have minimum education standards. They're all bound by conduct rules. They have high ethical standards and they have an element of social responsibility. So my question really is, should data scientists be left out of this loop? I think we should really be included. So first of all, I want to talk about the minimum education criteria. So there's three ways really in which people can learn data science skills. So there's usually the sort of gold standard is this institutional learning. People do maths degrees, engineering degrees, man Dewey's biology degree, but ends up in data science. Or you've got these online courses like Kaggle, Udemy, DataCamp, which I rely on so much for different skills and sort of just try to boost my skills. And on-the-job training as well. So if we just look at each of the three in turn. So institutional learning, they have often really wide curriculums. They're taught by academic experts. They have strictly controlled exams and coursework, so they make sure that everyone's achieving, and when they do achieve, it's above the line and all good. And they always have access to cutting edge research. If we look at online courses like Coursera and Udemy, they allow you to build your own curriculum. It's really hard to say with a Scottish accent. So they're often very, very hands-on, and they're usually inexpensive, which is great. Oh, wrong one. And then the on-the-job training, this is actually really, really good because it gives you the opportunity to work with really messy data, which is often not present in some of the sort of other courses. And you get access to sort of hardened experts who've worked in the field and done it. And often if you work for a big enough employer, there's usually a lot of budget to actually go in and do supplementary learning on online courses or even institutional stuff like which I'm going to be doing next week. So if we just circle back, in terms of the cons for each one, institutional learning, a lot of the material can be quite irrelevant. So I did a maths degree, but I can count on no hands how many times I've used axiomatic naive set theory. Never used that in my day-to-day life. They're often very expensive to do any courses. I think sometimes it's like £9,000, £14,000 to do a master's in data science these days. So the barrier to entry is pretty high. Institutions vary across the board, so you're not actually guaranteed. Although somebody does a data science degree, you don't know if that data science degree was mainly focused on engineering or mainly focused on modelling, or a mixture of both. So it's actually really hard to standardise because we haven't really decided on what is data science, and it means something different. In terms of the courses, so these courses, again, because you can pick your own criteria, they're really, really flexible. But again, the quality of the courses vary greatly. A lot of the time, if you don't know what you don't know, then it's hard to actually build your own curriculum. And also, a lot of these courses, they focus mainly on sort of the best case scenario. So you're working with data that's actually all nice and clean for you. You've maybe got to impute a few missing values, nothing too fancy. But in real life, it's never like that, and it's really difficult. And so they're not actually training you for when things go wrong a lot of the time. And then on-the-job learning, which is really great, but there's no guarantee that the people in your team can actually train you to what you want to do. It's often difficult as well to actually find time to do the training. And then also sometimes you're limited by the in-house technology. So if you work in a company who primarily use R, for example, but you really want to get into Python, you're sort of stuck. So it's really difficult. So because I started life as an actuary, I thought, what can we take inspiration from the actuarial profession? So the actuarial profession, if you don't know, have a series of exams that you have to pass in order to be an actuary. And when I was training to be an actuary, I think there was something like 14 exams you had to pass, as well as working full time, which was a nightmare, which is another reason why I didn't want to do it. But the good thing about the actuarial profession is they have a number of tracks in order to get you into the profession. So it's not just if you don't have a maths degree, you're out. It's actually trying to be quite inclusive. So the first track is for people who do have a maths degree or have a significant mathematical background. They can do this track. They basically join the company. They then sign up to be an actuary. They start doing the exams and away they go. The second track is for people who maybe didn't do very much maths as part of the degree, but they really want to be an actuary. So you can actually do these sort of entry-level exams where you basically have to prove yourself that you sort of cope with the level of maths that's going to be expected of you throughout the training programme. And then there's even a track for people who don't actually want to be actuaries. They maybe just want to be actuarial analysts. They want to work in finance. So actually they can do a subset of the exams and they sort of can just work their way through the exams and they become like an associate or an analyst through that track. And so the actuarial exams themselves are actually very well structured. The first bunch are sort of really focused on your technical skills. And they sort of cover things like modelling and accounting and sort of like mortality rates and all that sort of stuff. And then the next tier up, you're looking at sort of general practice knowledge. So it's more about, best practices for modelling, best practices for reporting, best practices for governance, that sort of stuff. And then sort of once you progress up the tier, you end up in this sort of industry-specific sort of territory where you maybe do a couple of modules on insurance or a couple of modules on pensions, that sort of stuff, or general insurance, depending on what track you pick. And then you've got a sort of specialist module. I think when I was doing it, it was called the SA modules, which were like these specialist modules at the top, which again is sort of a bit deeper into one of your practice areas. So I think when I was working at Aegon, for example, it was a pensions house, so I think they sort of funneled you down the pension side. So, but I think if you work for a general insurer, it's sort of specified by them. The interesting thing is with the actuarial profession is they also have a sort of real life work experience criteria as well. So even if you pass all the exams, you still have to prove that you've worked as an actuary or a trainee actuary for at least 3 years. And the last year has to be whilst you're passed onto that last tier. So it's quite interesting that you can actually devise this structure that's relatively inclusive, but also guarantees a sort of base level. Everybody's coming in at the same level of knowledge. And I think taking inspiration from this, I think would be really good if we could maybe devise an exam-based structure or at least something that just sort of guarantees that when you recruit a data scientist, you know you're getting quality, you know you're getting high standards, everybody understands what they're doing. So the other three, in terms of conduct rules, ethical and social responsibility, they're all quite similar. So I've decided to sort of lump them all under one thing. And it would be great if some company or some organisation had really took the initiative to try and help us or guide us through this sort of maze. And luckily for us, we have, which is great. So the Institute and Faculty of Actuaries, along with the Royal Statistical Society, have come up with this in 2019, which is a guide for ethical data science, which is really just this framework that they've ultimately boiled down to 5 points. So they look to seek to enhance the value of data science for society. So really this is all about trying to make sure we're always looking for opportunities that we can positively impact people's lives and society. Number 2 is quite obvious, avoid harm. So often as data scientists, we employ a lot of techniques that maybe optimise for profit. But really the question is that really the right thing to do all the time? Because optimising for profit could actually drive you to unfair customer outcomes, which is obviously really bad. There's also, if you work in industries, maybe, I don't know, working in the gambling industry, for example, and trying to encourage people to come back and come back and come back, is that an ethical thing? Is that a moral thing? It's just things to think about. But again, it's just understanding the impact that your models have on society as a whole. The next one, apply and maintain professional competence. So that's sort of linked to what I was talking about at the start. A lot of the techniques we do employ are really technical and really difficult to understand. And I think the most important thing we really need to understand is the limitations of what we're doing. And I think that would sort of separate you from the sort of wheat for the chaff, if you like. The guys who totally understand these are the models and these are the limitations of the models that you're putting live. I think that's the main thing here. And then if we look at the last fourth, so seek to preserve and increase trustworthiness. So what I found for this particular one is taking people on the journey really, really helps. So data science is really complicated, especially for non-technical audiences. So we found, instead of going all guns blazing and saying you should employ this neural net and it's going to be amazing to solve this problem, start basic, and you can maybe start with some linear model that will actually it's really explainable, and you can actually give the guys a really nice interface, even in Excel, that allows people to flex the inputs and see the outputs, and they can start sort of testing for themselves, like, okay, well, if I move this, then that changes this and that changes that. And it just helps to sort of create that level of trust and transparency in what we do. We should never try and dazzle people with science. And the last one, maintain accountability. Maintain accountability and oversight. So this one really boils down to model monitoring and model monitoring documentation. So it's just making sure that when you put a solution live, you really understand that it's always doing what you think it was going to do. So just making sure that it is predicting what it should be predicting, make sure it's sort of tracking well and it's actually being used for its intended use. So we're in this age of sort of hyper-personalization where we look at personalized advertising and content experience, pricing. But I think with this level of personalization, we really need to be careful that our models and the decisions that we make are not inadvertently causing harm or disadvantage to subsets of society. So I'll leave you with this quote from Spider-Man. It's not the usual quote for Spider-Man. Intelligence is not a privilege, it's a gift. And use it for the good of mankind. So data science is really much more than choosing the right libraries and packages. It's really a powerful force for good when it's governed appropriately. Thank you. That's you.
Okay, hi everyone. My name is Jana Kuncheva, and today I'm going to tell you about the role of data science in drug discovery. So first I'm going to tell you about who I am and what my experience in the industry is. Then I'm going to tell you why data science should be beyond packages and libraries from a drug discovery point of view. And to do that, I'll have to tell you how the drug discovery industry works and how can data science essentially disrupt the causal pathway that underlies the drug discovery process. Then I'm going to tell you what the role of a data scientist in the drug discovery industry should be, and I'll also give you some examples of Optima's R&D efforts in the drug discovery industry. So I did my bachelor and master's in mathematics and statistics at the University of Warwick, and then I went to do a PhD in mathematics at Imperial College. I developed different mathematical and machine learning methods for the analysis of genomics and neuroscience data. Then I left academia and joined the industry, and I worked in 2 small drug discovery companies for almost 6 years. I just recently joined Optima as a lead data scientist in the health section department, and I'm very excited to contribute to its efforts in the health sciences. So, in my belief, from a drug discovery point of view, the data scientist should be at the heart of a cross-collaborative effort. And I have identified 5 different stakeholders in the drug discovery industry that the data scientist needs to collaborate with and find a way to work in a 2-way approach. These are biologists, chemists, business development folks, drug manufacturers, and clinicians. However, for a data scientist to really add value in drug discovery, they actually need to understand how the drug discovery industry works. And this is why I'm going to tell you now a little bit more about that. So the drug discovery and development process is a very long, complex process that takes more than 10 years. And it starts with the target discovery, which is essentially trying to identify genes that potentially cause a disease. And once you identify such a gene, you enter a preclinical assessment stage where you try to see in some cells or in some mice whether targeting the gene is going to kill the organism and is there any potential for a drug. If everything goes well, you enter a clinical development stage, which consists of 3 phases of clinical trials in humans and in animals. And if all goes well in there, you send your results to the regulators and they decide whether your drug gets to the market and essentially reaches the patients. Now, many of you probably remember the very recent success of COVID-19, where we had a vaccine like within a year and a half. Sadly, this is an exception to the rule. And the process remains a very long one, a very complex one. One major issue is that around 90% of development projects fail to win approval. And the impact of that is that the average cost of a drug to reach the patient is estimated to be around $2.6 billion. And for a data scientist in this context, it's very important to appreciate the impact of every single decision they make in the early stages of the clinical development process and the motivation to derive an appropriate data-driven solution. So, how can data science actually help disrupt the causal pathway that underlies the drug discovery process? So the causal pathway assumes, sorry, I'll just use a pointer. Yeah, the causal pathway assumes that if there is something faulty happening in our DNA, it would get transcribed into our RNA. And this mistake will then get translated into the proteins, which actually tell our cells what to do. And if our proteins and cells don't do what they're supposed to, you might develop a certain intermediate phenotype, such as high blood pressure, which eventually will most likely result in indications such as a heart disease, heart attack, or a stroke. So the assumption here is that if we manage to disrupt this causal pathway somewhere early on in the process, we might be able to alleviate the symptoms of the disease or even cure the disease. Now, in the last 20 years, with the explosion of data, advancements of technologies, and the data storage capabilities, we have been provided an opportunity as data scientists to disrupt the causal pathway and really add value to the drug discovery process. However, again, context is key. The data scientist needs to evaluate which problems in this causal pathway they can actually use a data-driven algorithm on, and the choices that they make cannot be made in isolation from the stakeholders. The biologists, the chemists, the clinicians, they all require understanding of the methodological processes, why were they selected, and how the results are interpreted and integrated into the process. So, some examples of data and challenges that arise from it that we can address as data scientists. Genotyping data, for example, for 500 patients, it is around 4 gigabytes of data. More modern technologies such as next-generation sequencing result into 3 gigabytes of data per patient. The mathematical challenges that arise from that is that we need to analyze high-dimensional sparse data, and we also need to produce a high-dimensional variable selection procedure. The transcriptomic data into which the DNA translates, for example, can be recorded in different ways. One way is gene expression data, which can be recorded in more than 100 tissues and for more than 1,000 genes. On the other hand, single-cell RNA data is recorded in more than 100 tissues and in around 200 cell types. Other people collect DNA methylation, which is recorded into 28 million DNA sites for more than 100 tissues. There is many other types of RNA for which data is recorded in a similar manner to address different types of hypotheses and to validate them. The mathematical challenges that arise from this data, for example, are high-dimensional data integration and high-dimensional variable selection. Proteomic data is similar. We have up to 400,000 proteins in our body, and we can collect data for them from, again, more than 100 tissues. We can also record the protein structure of these proteins in the different tissues. And we can also collect information for the protein-protein interactions that occur between these proteins in different cells and tissues. And again, very similarly to transcriptomic data, challenges that arise from here are high-dimensional data integration and complex network analysis. Last but not least, health records data has been exploding lately because now we are able to collect this data electronically. And the data that consists is your family history, your medical history, any scans that you have done, any imaging such as mRNA, your diagnosis, any lab tests. And all of this data is right now collected over time, and essentially what you end up with is data for hundreds of millions of patients, and for each of them you have multiple data points for potentially thousands of phenotypes. The Challenges that arise from that is, again, we need to analyze a high-dimensional, very sparse data set, and we need to account for the longitudinal aspects of that data set as well. However, if we address those challenges, we can actually identify the best patients for our clinical trials. So there have been huge efforts by biobanks to actually attempt to capture all of this data from the causal pathway from the same exact cohort so that they can enable the most optimal way for exploring the data and understanding what causes the diseases and what are the effects of diseases. Examples of such biobanks are the UK Biobank, Biobank Japan, or the FinGen Biobank, and there is many more. However, as data scientists, we again should not forget that context is key. The data scientist needs to evaluate how to link this different type of data sources if they want to use one of those biobanks. And they can do that using basic or advanced statistical modeling or even machine learning methods. And the choice will enable us to disrupt the causal pathway. So to conclude, data science can efficiently leverage all of this available data to disrupt the causal pathway and to optimize the drug discovery process. And it can do that by doing three things. One, understanding actually how the drug discovery industry works. Two, putting the problem into context. And three, communicating efficiently with all stakeholders in the chain. So now, going back to the beginning of my presentation, and in light of you understanding maybe a little bit better how the drug discovery industry works and how we can, as data scientists, contribute to disrupting it, I'm going to tell you what I believe is the role of the data scientist through some real-life examples. Again, to highlight, I believe that to add most value and benefit to the drug discovery industry, a data scientist must lie in the heart of a cross-collaborative effort. And today, I'm going to show you and talk to you about some examples between the collaborative efforts and work that biologists and data scientists do together. I cannot go through all of this type of collaboration, sadly. So the first and very important aspect is hypothesis generation. Many times I have biologists that come and ask me, oh, I know that this gene is involved in this certain biochemical process. So can we assume that it also causes a certain disease? In this situation, we actually need to sit down, design a study, and experiment to test the hypothesis that he has just presented to me. Then biologists and data scientists also work together on data assessment and data collection. The biologists many times ask, well, do we have actually data to test our hypothesis? I have discovered this amazing publicly available database. Can we use it? In this situation, the data scientist has to actually sit down, evaluate the data set, decide whether it will really help validate the hypothesis, if needed, normalize it, or if identifying that the methods used to produce the database were not good, maybe go back, reanalyze the raw data, and use it to make sure that the hypothesis testing is done correctly. And of course, the most exciting aspect for a data scientist to work on with biologists is the data analysis. So biologists many times ask me, can you tell me if there is an association between a gene and a disease? And genome-wide association analysis is just one way to answer this question. They also ask me, well, can you tell me actually which genes are associated to a therapeutic area as neurodegeneration, for example? Then I might go and use a colocalization analysis to answer their question. A third and very important question they ask many times is this gene causal of the disease, or is it actually symptomatic of the disease? And Mendelian randomization is just one way to answer this question. However, many times there do not exist off-the-shelf solutions to answer the question of the biologists. And this is when, this is the job of the data scientist to either develop a new method that can validate the hypothesis, test the hypothesis, and answer their question, or adapt an already existing method so that they can provide the biologist with a solution. Last but not least, results interpretation. This is absolutely important, and I don't think that a data scientist working with biologists can go without that. Many times they ask me, so these results look great, so how can we use these results to validate that my gene is actually also a good drug target? In this situation, as a data scientist, you need to communicate results to a non-technical audience. You need to explain them what the results mean, how they validate the initial hypothesis, and how they can integrate them into a further validation of the gene as a potential drug target. This is also the time to think about whether you have validated your initial hypothesis. If you have not validated it, maybe you need to redesign and do the analysis again, or your hypothesis is wrong and you need to change your hypothesis. So this is the 4 different aspects the data scientists and biologists work together for. And I'll just briefly tell you about Optima's efforts to work and contribute to the drug discovery process. So Optima research and development efforts contribute to the drug discovery process because we have identified multiple questions arising from the early phase drug discovery industry that still don't have a solution. We have provided mathematical and developed new mathematical methods that answer those questions. We have applied them to multiple different data sets that highlight different aspects of these data sets. And then we have published them together with some collaborators, for example, from MIT into journals as Nature. We have also evaluated their applicability and their impact with a huge cohort such as the FinGen one that I mentioned earlier. The objective of Optima is to not to publish so that we can make available all these methods for anybody to use, but also we have been developing some of those methods into software together with Mandrill as products in the hope that people will use them and will make them even more easier for the general audience to use, but potentially there might be people that want us to take those methods, further develop them for their needs. For example, they might have a specific technology, or they might have some specific aspects of their data that they want us to adapt the product and deploy it in their in-house pipelines. So, to conclude, as you see, the drug discovery industry poses a number of challenges for the data scientists, and today we have just scratched the surface. What I really want to highlight is that solutions in the drug discovery industry are not based on packages or libraries or specific algorithms. They're mainly based on the approach of the data scientist. The data scientist must be aware of their surrounding. Context is absolutely key here. And furthermore, hypothesis generation, testing, and scientific design are at the heart of the solutions. Without a well-defined hypothesis and without a good scientific design, you have 0 chances to get your drug target being progressed forward, or maybe incredibly low ones, like someone just decides to gamble on it. At the end, I just wanted to highlight a moral aspect. If you're a health data scientist, the ultimate goal is to help the patient, so just keep that in mind. So thank you for your attention, and that's it.
Thank you very much, guys. That was great. I'm going to kick off the Q&A. But if you've got a question, just raise your hand and I'll pass you the mic, just for the viewers online. Does anybody want to kick us off? Oh, here we go. There you go, Dan.
I'll kick off. Thanks a lot. Really engaging conversation, actually, from 3 very kind of different aspects of data science and how it relates to the way that we live. We live in a world of open source knowledge of any kind, be it media, be it Wikipedia, be it code. So what's your advice to a data scientist around the trustworthiness of open source libraries and packages? You know, I come across a new package and this looks cool, it does what it says on the tin. What's your advice to maybe not a seasoned data scientist, but somebody who's either junior or early on in their career around curating the trustworthiness and the integrity of libraries and packages that they want to use?
I can speak up because I have worked with open source code. It's not great, but it's open source, so you can read it. And if you spend enough time understanding it, this is exactly what it does. You should then trust it and apply it. But most of the time, at least open source code for the drug discovery industry and genetics in particular is not amazing. So if you decide to use it, you should be prepared that there is a lot of deployment issues that you have to be tackling.
Can I add something from a different point of view? So as a contributor, as a data scientist, you should always contribute to the open source community, and you don't need to go and write a package to do this. You can go and leave your opinion on Stack Exchange, for example, right? Because data scientists or any computer scientist, 90% of the time you're actually searching Stack Exchange rather than writing your own code. So there's another way to do this. You should contribute, and that way you can actually build up your credentials, and when the time comes when you publish your own package, you will also have already have built some credibility in the community if you do that.
Just doing a bit of research around the subject as well, because I know, like, if I can't find an article online that's on toward data science or something like that, somebody's not written a sort of lengthy sort of review of the package, if you like, then it's one I tend to like maybe not use for production strength stuff. So I think it's just doing a bit of reading and just testing the code and making sure it, have an idea of what you think it should do and make sure that it actually produces what you think it should do.
And obviously, you should use trusted sources. So if you are into R, always grab a package from CRAN, because they implement standards rather than actually going and cloning a GitHub repository and using it in your production system. So.
Yeah, so it's just actually to follow up on that question. It's why would you trust closed source? You've got absolutely no reason to trust closed source. At least with open source, you can check it yourself if you need to, or if you can't, you can look at a community to check it for you and get their results back. But with closed source, you're just taking what somebody's told you, essentially. So it's a question that comes up: why should you trust open source? It seems all the way around to me.
I have an example for this. So when I was at Tesco Bank, I didn't work directly on the project, but somebody actually implemented a machine learning algorithm in a closed source system. And this algorithm actually had a bug. So we discovered this, and it was a long process to go back to the source, as in the owner of the code, for them to get the bug fixed and release it. But it wasn't a high priority bug. So you were waiting quite a long time. It was high priority for us, not for them. So, yeah.
Have any other questions? I've got one for the time being. Angela, so on the market at the moment, machine learning engineering. So for data scientists out there who are more research heavy and statistical heavy, you talked about picking up version control and unit testing and software engineering principles, but if somebody wants to make that transition, how is the best way to go about that? Are you picking them up on the job at the moment, or would you go and do online courses?
Bit of both. I think you should go to somebody like DataCamp, who have designated courses for, as in software engineering for scientists. And those courses will teach you the basics, and then you can learn the rest yourself. It's not that tricky. You might get scared of it, thinking about it, but it's not that tricky. You just need to get the basics right. And to get the basics right, you should consult a course like that, and then take the rest by yourself.
Perfect. And then one for Scott, you're recommending the online courses. So there was a chap I was speaking to earlier on in here who done a PhD, or maybe was in education, they've done a lot of maths and stats, but went into engineering, but different form of engineering, but wants to transition into data science. Was there any recommendations of the online courses that you would like the Udacity, or any specific ones that you would say is go and do programming at this course or another sort of module at another?
Yeah. So I think Coursera, it's actually really good, or it's one I've used most often, I'd say, because especially if you've already got a background in sort of maths anyway, they offer a lot of good courses from really reputable sort of sources as well. So that you're getting like MIT and you're getting Stanford and you're getting things like that. So I think at Coursera that the quality of the courses are really, really high, and you can basically flex how complicated you want the courses. So Andrew Eng's courses, his courses are great, but they're very technical. But they're really good if you want to get the really nitty-gritty nuts and bolts of what you're doing. But there are sort of other ones. But yes, I think I have noticed that things like Udemy, I think, have been really good. So I was working on a project using reinforcement learning recently, and I used Udemy quite a lot just to get my foot in the door and just get me to the level of understanding where I could start playing with things myself. So you don't have to finish the whole course. I think it's just getting you to a point where you're comfortable to have a play and start doing things on your own, and just getting familiar with the terminology. I think because reinforcement learning's got its own sort of whole host of terminology that comes with it, and so it's just getting you used to the terminology really. And
it's getting a lot more common. So a lot of data science managers that I work with, they really like to see it, that people have went and done the self-learning and done the courses, and so many data scientists nowadays put those certifications on their CVs as well. So
it's just what I'm seeing. And the thing as well is that a lot of these courses, they focus on the best case. So it's like, well, what if linear regression doesn't work? Or what if logistic regression doesn't work? Or what if you're in a situation where just linear models in general don't work? What do you do? Do you just reach out and start building some 16-layer neural network? Like, is that the right thing to do? I don't know. But it's just, but even like in a business setting, it's like a lot of the time, like Kaggle, for example, everybody is like trying to squeeze as much AUC out of these models as you possibly can get, and like you say, layer in doing those ensemble models. But if you work in a business, people are not interested in getting the absolute best performing models. They're really looking for, can you explain to me what this model's doing? Is it getting me roughly 80% of the way there? And like tick. So it's actually like looking for a sort of this blend is sort of a mixture of explainability as well as performances. Yeah, so it's an interesting one.
perfect. Any more? Go on. I brought my own rules. Ask the question without the mic.
Hi, it's probably more a question for yourself, Scott. When you talked about a data science governance body, my question would be around that, and Chris touched on that a little bit already, is what is a data scientist? Because we hear a lot of new roles coming into the field, about engineering, and obviously yourself, you spoke about how much data engineering should a data scientist do. So how would you define a data scientist within that governing body? Because my initial reaction to that part of your talk was that it felt a bit like gatekeeping. So if you were going to have a body like that, who can be a member, I suppose, is my question.
Yeah, no, it's a tricky one. Because I think in my eyes, I mean, it's probably a bit, I don't know what to say to you. Yeah, you can go.
So, for example, the Royal Statistical Society has different types of chartered statisticians or graduate statisticians, or even they have a data science track now. So you need to provide a series of educational or job-related experiences, sort of as a portfolio, plus a certain amount of hours you have spent the last 2 years, plus recommendations to show that you're an active statistician or data scientist and you deserve the data scientist statistician title or the charter statistician title or the graduate statistician title. Many people actually look for consultants through the catalog of statisticians in the Royal Statistical Society, and they have also data science track, I think, in the last 2 years. The question is, should it be only in the Statistical Society? Shouldn't it be a collaboration effort between also the mathematical and the computer science, or, I don't know, have its own society?
Yeah, it's tricky. Because I think, you want to obviously make it as inclusive as possible, but at the same point, you wouldn't want any man and their dog being a doctor, for example, and doing surgery on you. You want somebody with a level of proficiency. So it's like, how do you guarantee that level of proficiency without just getting sort of cowboys in and just sort of any old person that's done a Kaggle course and thinks they're amazing? I've come across people who've read one book and they're calling themselves a data scientist. It's a hard one, but in my eyes, at least, the data science is more about the sort of like the scientific method and about the statistical models and the sort of more modelling side. Whereas I think you bridge the gap between the sort of engineers and. But I think to your point, I think it's really good that data science, who have got the statistical knowledge and the scientific experience, still understand a bit of your world, because, like, say, when you come to hand something over, if we didn't have a clue, then your job's a nightmare. So it's... That's right. I mean, you can end up building a model that can never be deployed. Yeah. So, and then there's no point building that model. So, I suppose there should be different classes of data scientists. Some that are kind of very senior, and they should understand the mathematical background of what's going on, so they can validate other people's work.
and there should be other data scientists who can build models and explore the area. There should be other data scientists who are good at putting this stuff into production. So probably different tiers.
Do you wonder whether you should almost have like a data science like apprenticeship scheme sort of thing? Because I mean, you don't have to, like say, because price is sometimes, or cost is sometimes such a barrier to entry. People can't afford to do masters or can't afford even to do the first degree if they live in certain countries. So it's like, if you have a sort of population of data scientists at your company that are really good and know their stuff and know their technical stuff, you should be able to sort of bring people a bit junior and sort of train them up within the confines. And like I say, but then if there's an evidence-based thing like the RSS has got, you could then build that portfolio within the company and submit it. And so you're not like saying, you've not got a master's degree, you're out, that's it. But building up that portfolio and building up that trust and credibility, like you said, on your contributions. And
I think even in the GMC, you can become a consultant with experience. You just need to build a portfolio. You don't, there are two ways. You can do the exams to become a consultant doctor, or you can gain experience and submit your work and get that approved. So I think that's what, Scott is suggesting. Yeah.
Back to one of the points, what we are seeing in the market is a lot of companies are differentiating the roles as data scientists being statistical and research side and building proof of concept models and building statistical machine learning algorithms. And then ML engineers are still doing that part, but working on the deployment side. So they're kind of, have got the software engineering skills and have got the production experience. I think that's more and more becoming quite commonly used. Not for everybody, but it's definitely a trend.
Bigger companies.
Bigger companies. Yeah, probably, most likely, probably time for one last question if I've got one more. Yeah.
This is more for maybe the drug discovery side of things. So you touched on it earlier, explainability. Do you face that kind of problem where, it seems quite a high stake proposal where you maybe can't explain what links there were? Do you face that problem when you're going forward with your proposal that you've maybe used a neural network or something and you can't quite have that explainability?
To be honest, you don't need to use something as advanced as a neural network not to be able to explain the results. I have had that with much more simpler, unsupervised machine learning approaches. And it is very hard to drive this result forward. I did have it with my first company when we identified some very interesting subgroups in Parkinson's disease, but we didn't have the resources in-house to actually validate their meaningfulness and their biological interpretation. And because they were so novel, there was nobody else that had discovered them, so that we validated this makes sense. So we had to explore various different types of collaborations with different chemist groups and different biology groups outside of the company that do explore similar approaches so that they can integrate our findings into their experiments and try to validate whether these results make sense. They still haven't discovered, it's been 4 years later, I know that they still haven't discovered if this is something that could be integrated or not, but this is also how the drug discovery industry works. And it's very sad because you see an opportunity in your findings and you see the impact they could have, but it's so hard to get them to the point where they can actually be deployed in a drug discovery production. Yeah.
Thank you.
Thanks again, guys. I really enjoyed that. I think everybody did. It's great to see so many faces here again. And yeah, everybody's welcome to stay around, having a few more drinks if you want to. Cheers. See you later.